Let's start with one of the most important concepts in Spark Lineage. When Spark creates an RDD, it doesn't just know that the RDD exists, it also keeps track of how that RDD was created. So Spark knows things like, where did this data come from? Which parent RDD was used? Which transformation was applied? And importantly, if something is lost, how can it be created again? That's what we call lineage. Now, one very important point, lineage is not the actual data. Think of lineage like a recipe. If I give you a recipe for making a dish, the recipe isn't the dish itself. It tells you how to create the dish. Similarly, Spark stores the information needed to recreate the data rather than simply storing another copy of every intermediate dataset. So let's take a very simple example and see what this history actually looks like. Suppose our input is a file. We read that file using text file function, which gives us RDD1. Then we apply a filter function, which creates RDD2. Then we apply a map function, which creates RDD3. Now, imagine your Spark. You don't just say, I have RDD3. You remember that RDD3 came from RDD2 using map, and RDD2 came from RDD2 using filter, and RDD1 came from the input file. So Spark has effectively remembered the entire path used to produce RDD3. That path is the lineage. But why does Spark need to remember all of this? The answer becomes clear when something goes wrong. We're running Spark on a distributed cluster, so failures can happen. An executor can crash, a machine can disappear, network problems can occur. Imagine our RDD has 4 partitions, and partition 3 is lost. What would be the simplest but most expensive solution? Recreate the entire RDD. But Spark doesn't need to do that. Because it knows the lineage, it can ask, how was partition 3 created? And then it can recompute the missing partition by following the required lineage. So Lineage gives Spark a way to recover from failures without having to treat the entire dataset as lost. And this brings us to one of the most important characteristics of Spark recovery. It can work at the partition level. Let's make the previous example much larger. Imagine an RDD has 100 partitions. Only partition 73 is lost. Spark doesn't say, okay, let's rebuild all 100 partitions. It identifies the missing partition and determines how that particular partition was produced. So the recovery is targeted. The other 99 partitions are not recomputed. This is what we mean by fine-grained recovery. The important idea here is not just that Spark can recover, it's that Spark can recover only the part that is actually missing. Now we know why lineage is useful. Let's see how Spark represents this history. Spark represents these relationships using a graph, the Lineage DAG. DAG stands for Directed Acyclic Graph. Don't let the terminology make this complicated. At a basic level, it simply means the graph represents relationships between datasets and the direction in which those relationships flow. So if RDD2 is created from RDD1, we have a relationship from RDD1 to RDD2. And if RDD3 is created from RDD2, we have another relationship, from RDD2 to RDD3. The word DAG has 3 parts, so let's quickly understand what each one means. First, directed. The graph has a direction. Data flows from the parent dataset toward the child dataset. For example, RDD1 is followed by RDD2, and RDD2 is followed by RDD3. The arrows represent the direction of computation. Second, acyclic. A cycle would mean we could eventually come back to a dataset that's already an ancestor. For example, RDD1 leads to RDD2, RDD2 leads to RDD3, and then RDD3 leads back to RDD1. That would create a loop, and Spark's lineage graph doesn't work that way. Finally, it's a graph, because multiple datasets can be connected through these relationships. For example, RDD1 can lead to both RDD2 and RDD3, and both of them can then contribute to RDD4. That's what makes it a graph, rather than just a straight line. So, directed plus acyclic plus graph gives us DAG. Now let's see how this graph is actually built when we write transformations. Here's something very important about Spark. Transformations are lazy. So when I write RDD2 by applying the filter transformation to RDD1, Spark doesn't immediately process all the data. Instead, it records the operation. Then I create RDD3 by applying the map transformation to RDD2. Again, Spark records that relationship. So before the actual data processing begins, Spark already has information describing how RDD3 should be produced. And when an action, such as the count operation, is eventually called, Spark can execute the required computation. So what exactly does Spark remember when we define these transformations? For Lineage, Spark needs to maintain enough information to understand the relationship between datasets. At a high level, we can think of three important pieces of information. First, who is the parent? Second, what transformation was applied? Third, what is the dependency relationship between them? So for our example, Spark knows RDD2 came from RDD1 using filter function, and RDD3 came from RDD2 using map function. This is what allows Spark to understand how the data was produced. But there is one more level that's particularly important for recovery: partitions. An RDD isn't one giant block of data. It's divided into partitions. So when we talk about recovering an RDD, Spark can reason about individual partitions. For example, if RDD2 partition 3 was produced from RDD1 partition 3, Spark can identify that relationship. This is important because recovery doesn't necessarily mean recreating the whole RDD. Spark can identify the particular partition that needs to be recreated and trace its history back to the required parent data. Now, you might ask, why not simply keep copies of all the data instead of remembering how to recreate it? One way to protect data in a distributed system is replication. For example, keeping 3 copies of the same data. That helps with reliability, but there's a cost. Multiple copies require additional storage, memory, and network resources. Spark takes a different approach for intermediate data. Instead of continuously maintaining multiple copies of every intermediate dataset, it keeps the transformation history, the lineage. If data is lost, Spark uses that history to regenerate it. So the fundamental idea is replication stores copies. Lineage stores the recipe for reconstruction. So why was this approach attractive for Spark? Think about the cost of replication. Every time we maintain another copy, we're continuously paying a constant cost: high storage overhead and more data movement across the cluster. But failures are not happening every second. Most of the time, the data is being processed normally. That's why Spark's approach flips this around. With Lineage, Spark avoids the constant storage and data movement cost of maintaining multiple copies of every intermediate dataset. Spark only pays the recomputation cost on failure, not all the time. And because it isn't tied to a fixed storage overhead, this approach scales for large data far better than replication does. So the trade-off, right here on screen, is the whole story. Spark accepts some recomputation work during failure in exchange for avoiding the continuous overhead of maintaining multiple copies. That's particularly valuable for large-scale distributed processing. This design gives Spark several advantages, but Lineage isn't perfect. Let's look at both sides. There are several advantages to this approach. First, lower storage overhead, because Spark doesn't need to keep multiple copies of every intermediate dataset just for recovery. Second, fine-grained recovery. If a particular partition is lost, Spark can focus on that missing partition. Third, efficient resource utilization, because Spark isn't constantly maintaining unnecessary copies of intermediate results. Fourth, scalability. This model works well as Spark scales across large distributed workloads. And finally, automatic recovery. Spark handles all of this without manual intervention. So Lineage gives Spark a relatively lightweight way of knowing how data can be reconstructed. But there is a trade-off. If Spark has to reconstruct something, it has to perform computation again.
The biggest limitation is straightforward. Recomputation takes time. If the lineage is short, this may not be a big issue. But imagine recreating a partition requires going through a large number of transformations. Now recovery can become expensive, which affects recovery time. There's also a source dependency. For recomputation to succeed, the required upstream data must still be available in order to reconstruct anything downstream of it. And as the lineage becomes more complicated, Spark has more dependency information to manage, which adds scheduler complexity. So Lineage is efficient, but it isn't free. And this becomes particularly important when Lineage keeps getting longer.
Consider a long-running or iterative workload. We might have RDD1, then RDD2, then RDD3, and eventually RDD100. The longer this chain becomes, the more computation Spark may need to perform during recovery. There can also be more lineage metadata and more scheduler overhead to manage. This is where checkpointing comes into the picture. At the level we need for this section, think of checkpointing as creating a new recovery starting point. Instead of having to go all the way back through RDD1, Spark can use the checkpoint as a starting point for future recovery. So checkpointing doesn't replace the idea of lineage, it helps address the problem of lineage becoming too long. We'll go into checkpointing itself in much more detail in the dedicated checkpointing section. For now, just remember its relationship with long lineage. Now let's bring everything together and see how lineage contributes to Spark's fault tolerance model. Let's put the entire concept together. Suppose an executor failure causes a partition to disappear. First, Spark detects that the partition is missing. Then it examines the lineage. From the lineage, it determines which parent data was required and which transformations produced the missing partition. Spark then re-executes the necessary transformations and recreates that partition. So the key idea is, lineage is the transformation history that tells Spark how data can be recreated. It is metadata, not the actual data set. Spark builds this history as transformations are defined. The lineage forms a DAG, showing relationships between datasets. Because Spark can reason at the partition level, recovery can be targeted rather than rebuilding everything. The major advantage is that Spark avoids the constant cost of replicating every intermediate dataset. The trade-off is that very long lineage can make recovery expensive, and that's why checkpointing becomes useful when lineage grows too large. So if you remember just one sentence from this entire section, remember this. Lineage is Spark's recipe for recreating lost data.